One thing we want to talk about with gas laws is the fact that there are other applications for the gas law. Namely, that the gas law at any given time, right, is going to be four variables and one constant, right? So what this means is that PV over NT is going to be equal to some constant R, the ideal gas constant. Now that gas constant is going to be constant at any time. What this means is that at two different conditions, we'll be able to use R to relate those two conditions to each other, right? So what this means is that at any given time, if condition 1, I have pressure, volume, moles, and temperature, that means that at any given condition 2, these things are going to be equal to R. So what this means is that I have a relationship now that's set up between these two conditions, these two different conditions, two different times, right? So what I can do is, since both these R's are the same, they both equal R, I can just set them equal to each other. Right? So I will have these relationships. Now, it's unwieldy in science to set up something that's going to have four variables involved in a system. So what we like to do is, instead what we're going to do is control variables within the system and set them equal to each other. Okay? So if I say that in this condition, we're going to keep the same pressure for each one of them. If P1 is 1 atmosphere and P2 is 1 atmosphere, both of them are 1 atmosphere. That means that they're going to be equal. And what that means is that P1, right, is equal to P1 here, right? Because P2 is equal to P1, so I can say that they're both P1. What that means is that in this case, I can divide by P over here, and in doing so divide by P1, that means divide by P1. If I keep pressure the same, things cancel, right? So that now reduces it to a 3-variable problem where I have V1 over N1 T1 is equal to V2 over N2 T2. Okay? If I control another variable, like I keep the temperature constant, if T1 is equal to T2, then that means T2 is equal to T1. Right? So the temperature is constant on both sides. That means I have a relationship now between V1 N1 and V2 T2. Okay? And this goes for any variables that I have in the system. If I constrain two variables so that they're equal on either side, I can form a relationship between any of the variables that are set up in the gas law. Okay? So it's important to know that if I've got two different systems and they're both gases, I do have this R value that will allow them to be set equally to each other. And that allows for mathematical manipulation, which turns out to be true experimentally. Okay? Right, and there's one more relationship that I want you guys to be familiar with, right? And again, it derives from the gas law. Right? And the gas law is PV, also known as terrible pen, PV, what am I doing? PV equals nRT, all right? Now what I can do is I can change this a little bit, move the variables around, right? And what I'm going to do is I'm going to isolate NV on one side. So P, that. So P over RT is going to be equal to N over V. Okay? Now I want you to recognize something. If I have an NV value, this is moles per volume. Does that sound familiar to anybody? Moles or volume? Moles over volume, say liters. All right? That's a molarity function. Okay? In addition, what I can also do to manipulate this is I can use molecular weight. I can multiply this by molecular weight. And that gives me a little bit of flexibility. If you remember, with molecular weight, okay, the molecular weight of anything is equal to the grams of the substance over the moles of the substance. And this is equal to molecular weight. And what I'm going to call that, instead of using molecular weight there, I'm going to use a special term. The book uses something that looks like m here, but in this case, it's going to be fancium. So I got fancium there, and I'm going to multiply fancium across both sides of the equation. Right? And I can do that. So I'll multiply this. I'll put fancium here and fancium. Go ahead and say that. Right? If you had a test, be like, oh no, I have to use fancium. Okay, fancium is down both sides. Now, if you remember, fancium is equal to grams over moles. Do we have a term here that's also moles? And we do, and that is N. Okay, so if I look at this fancium, okay, another way to write this is to write this as grams of substance per moles of substance. And since I'm using N for moles, I'm going to change moles here to N. Okay, what's going to happen? Yep, you called it. The N's cancel. All right. So now I've got something that's a little interesting. Now I've got molecular weight times pressure over RT, and this is equal to grams over volume. Okay, and if the grams over volume, and the volume is a liter at this point, so if I have grams over liters, if that scratches your brain, you're like, I remember that from my chapter 1. Way back in chapter 1. Oh, back when I was much younger. Okay, back when you're in chapter 1, grams over volume at that point. The grams over volume is a density measurement, right? Grams per liter is similar to grams per milliliter, but this is the gaseous density because gases occupy so much space. So gas density is grams per liter. So another way to look at this value is to say, oh, well, that's density. I'll put density there, all right? So now I have a way of manipulating the gas law. So I have a density, and I've got pressure, and I've got RT. Now I'm going to rearrange the equation. I'm going to move RT up here. So now I have d RT over P, and this is going to be equal to fancium. So the molecular weight of any gas can be found so long as I have the density and the gas law constant, look that up, the temperature and the pressure. Okay, so the density and the temperature and the pressure, the density can be looked up depending upon the gas, okay, or it can be given to you, or you can figure it out. You know, how much mass you have in a certain amount of volume, you can figure that out. Temperature can be measured, pressure can be measured. At that point, we can determine the molecular weight of any gas using this equation. Okay? So this is molecular weight of any gas. Alternatively, what we can do is we can look at this setup and say, well, I've got the molecular weight here, okay, and I've got density value. That means I can rearrange this and solve for density of any material at any temperature, okay, using the ideal gas law, so long as it's